This is a title billion task Parsl that I sort of came up with as a joke a month or two ago. And then some people liked it and I started thinking about things a bit more. So here's a futuristic scenario. It's the year 2032, which is 8 years in the future. Parsl is regularly running billion task workloads. So we can have a think about what do we imagine that looks like? What does Parsl with the code that we have now? Where's it going to break? What might we do to make this reality, this proposed reality come true? Okay. So what is a billion task workload? There's a few different ways in which we can think about that. So obviously it's big in the number of tasks because it's a billion tasks. But with that, some people bring along with them an assumption that maybe that means it's going to run with very high throughput, for example. Or a different view might be that you're not necessarily going to have very very high throughput, but you might be running for an extremely long time. Maybe there's going to be a lot of data pushing what we have. Maybe you imagine that this is going to be a workload that's so big it fills your supercomputer and you need to use two supercomputers, which is sort of the classic 25-year-old grid computing case that VDS used or VDS tried to do 25 years ago. Things like that. And I'm not trying to make a definitive list. What I'm hoping in this talk is you sort of stir up imaginations. I already added 1 point to this based on Yadu's comment, who asked, are we thinking about running something for many months? And yeah, if you run 6 months, billion tasks, that's 64 tasks a second, churning away in some pipeline. That could fit this. What are the things that are going to break? Well, pretty much I wrote down all the features I could think of in Parsl, and then I added a few other things on the end. But there's all different pieces that are going to get slammed in different ways depending on how you interpret what a billion tasks is. But there they are. It does kind of look just like the Parsl feature list. So not too exciting. So I thought I'd dig into a few topics that I imagined breaking and where I could imagine seeing things being improved. And then later on, I'll talk a little bit about some sort of social political issues rather than technical issues. So if you're imagining a high throughput workload, you probably imagine the high throughput executor. That's what it's called. And that's what it was originally implemented for. So what are a couple of extreme sort of execution scenarios for this? One might be if I've got 10,000 worker nodes and they can run 100 tasks at once and our tasks are 1 second long, that's 1,000,000 tasks per second. Right, so that workload is pretty insane. That would be saying our interchange and the data flow kernel would be processing 1,000,000 tasks a second. That's about 10,000 times faster than this code can run on my laptop. So we are definitely not there. Differently though, 1 billion tasks over 6 months. That's the thing Yadu asked about. That's only 64 tasks a second, pretty low throughput. HTEX can do this. There are some other problems you'd encounter, but pretty much you could write a for loop that runs 64 tasks a second and runs for 6 months. And I think Parsl right now should probably be able to handle that just fine. So what are some of the limits in HTEX? Well, if you want, you can replace HTEX completely. So you make some amazing super scalable executor. You can replace it in Parsl. That's fine. WorkQ's already got WorkQ is one of the big replacement executors. There's a bunch of them. But also inside HTEX, we haven't really pushed on it much. but there are swappable components if you wanted to push on things with your own implementations. So the interchange, there's one interchange for your workflow. So like I said, if you've got these 1 million tasks a second, that's all got to be running through one interchange, which right now looks like one process. It wouldn't necessarily have to look like one process if you wanted to, but that's going to hit. I actually struggle on my laptop to saturate that, but I think that's going to get saturated pretty easily as you scale up. And a worker pool is also swappable, and that's something we have done. So we used to have 3 different executors that were HTEX with different clothes on. So we had HTEX as it looks now. We had the MPI executor, the MPI something executor that looked like, no, the extreme scale executor, sorry. And that used an MPI based worker pool, and we had the low latency worker pool that I never knew what it did, but that used a different kind of worker pool as well. And
the low latency worker pool, just we ripped out all the stuff that was useful for like robustness and reliability. It was like a very, very bare bones HTEX.
Yeah. Okay. Right. So one of the scalability limits, for example, right now is the interchange. Every worker node connects back to the interchange, and it needs 2 file descriptors for that. So you end up with very many open network sockets on the interchange host. And I relatively frequently hit that limit supporting users now when they have a restricted number of file descriptors set in their environment. So there's scope there for doing fun stuff, I think. Like I said, we've done it before. We could do it again. Maybe you would add more hierarchy or something like that. As an example, one of my fun projects that I do at the weekend is I re-implemented the interchange in Rust, because that's a meme to re-implement everything in Rust. Should be faster, right? Because it's not Python, it's compiled. There's no garbage collection. Garbage collection in a queued environment like the interchange is especially degenerate. Nice static linking compiled code. Turns out it isn't faster, and I haven't really investigated why. And it actually turns out sometimes to be slower by a lot. And if the interchange isn't actually in our tests being a rate limiting point, why bother working on the interchange? And one of the things it would be interesting to know is when does that make sense?
So just on that one, I would say that's surprising to me, Ben. I mean, in the work that your Rust implementation of the interchange didn't accelerate things. My guess would be because we weren't actually, that's not the bottleneck. My guess is that we're probably bottlenecked on the DFK like Jamie.
My guts from looking at sort of top and process stuff is that this isn't getting anywhere near saturating, and I suspect I've got something horrible like a bad log line in there.
Did you see much of Jamie's presentation when he rewrote the DFKNC and did a bunch of Python programming and Python profiling, and was basically like our DFK just can't push tasks fast enough because of basically some inherent Python. Like some of the times we were talking about just to like create a Python data structure was so significant we couldn't.
So I did some quick profiling with just the. Okay, so let's say we want to create 1 million futures. It takes me about 5 seconds consistently on my laptop just to create a concurrent feature.
Let me get these language slides.
Okay.
I'm just about to sort of talk about some of this.
Okay.
Not all of it. Yeah. So this is the point Yadi was, or variation of the point Yadi was just making, right? How do you describe a workflow that is 1 billion tasks? So in Parsl now, we kind of say, well, describe all your tasks and then wait for them to all finish. And that probably isn't going to scale to 1 billion tasks. So I think Yadi, your number was like, it's in one of the comments up here.
Yeah, the number that I reported was like 5 seconds to create 1 million futures. Weirdly, on a login node, I was seeing 8 seconds to create 1 million futures.
Oh, that doesn't surprise me at all. Anyway, yeah. So basically, it's pushing the limits possibly to impossibility to imagine having a single workflow which has 1 billion concurrent outstanding tasks, right? So what do 1 billion task workloads actually look like? I was kind of hoping Christine would be here because I think she probably has some of the most experience in seeing people doing this at ALCF. But for example, does a billion task workflow actually look like a million much smaller mini workflows that are relatively independent and we can go through those in a streaming fashion, right? And are there language issues where we say, all right, well, I'm going to give you a Python generator that knows how to make these tasks, and Parsl is going to say, all right, I'm ready for another 10,000 tasks. Give me 10,000 tasks more, right? And then maybe you aren't trying to run a billion tasks, you're trying to run an infinite stream of tasks that happens to expire after a billion. But if you move to that sort of streaming mindset, maybe then there isn't any concept of describing all the tasks because it's a stream. So language issues there are, can you do that in a way that looks nice for a user? Like we have this language goal of trying to look like Python. So how far do we have to look less like Python than we do now? And there's a few other issues like, can we run this as a multi-process submission? So like Kyle said with Jameson's work, where just putting stuff through the DFK is really expensive. What about if you are so excited that you have 10 submit nodes all doing this? What does that look like? Perhaps. Who knows? Okay. The other thing is executing. Executing the workflow doesn't have to be done in Python. Plenty of our library stack isn't. There's Erlang in RabbitMQ and Globus Compute. For example, loads of C, I think Fortran in NumPy.
And this might.
Wait, now you use fine. Just
Oh,
wave
okay.
at me when you want me to unmute.
Yeah, I mean, this might be one of those places where, it made sense for Parsl to be like a very greedy style system where we generate all the tasks and then execute it. There were discussions in the beginning of like making everything lazy. And the advantage with the lazy generation is that you don't have to take on the cost of holding all the tasks in memory. This is one of those design things that, at this scale, it does matter and it does hurt us.
Yeah, right. So one of the things that I think is quite interesting is sort of exploring, like you could explore this at small scales, right? You could say, what does a workflow language look like? What does a Python-based workflow language look like that is generator based or some kind of lazy generation based language, right? And you can explore that at small scale to see what it feels like without having, you don't have to run it on a billion task workload. You can still try it out and see what the ergonomics feel like. Maybe stick it in front of the DFK and try that out with people, just like we have other front ends for the DFK. No. Right. So that's one of the imaginations, right? One of the imaginings. But I was talking about, we don't have to implement in Python, right? So Jameson did a DFK reimplementation a few years ago in C. Negative points for whoever allowed him to touch C, but whatever. I've done 3 different reimplementations of the interchange in 3 different languages just for fun. I think there's scope there for interesting things, but also the Python people have really working on making Python better. It's getting just-in-time compilation is starting to appear. They've got much more multi-core concurrency support is appearing. Sort of just as time passes, we're going to get free betterness just from being in Python and the Python runtime getting better. But over this sort of 8 years, I'm talking about languages will advance, right? If you look at the changes from Python 3.5 to Python 3.13, which is 8 years, there's been quite a lot, especially performance-related stuff in there. Loads of Python people are getting into Rust, and if it might come to a point where there's enough ambient Python and Rust programmers for it to make sense to do some stuff in Rust. There's a good sort of social technical reason to not do it, that you don't want to write your code in a thing that you can't then go and hire the people to do. But Python and Rust as a sort of pair of languages seems pretty big at the moment. What if the scientists change what they want to use as a language? So I see people talk about Julia or whatever, maybe if in 4 years' time some other language comes along, and then they're like, oh, well, now I want to write my workflows in this other language. Is there a space for all of the work that we've done with Parsl that isn't tied to Python to fit in there somehow? No. So I just got a sort of grab bag of other random things that I think might break, and they're sort of me imagining other things still. Serialization, it's part of our data management story, but it looks entirely unlike files. We don't do a huge amount of good stuff here. So some of our protocols are done with Python pickle, and all of our Python objects, our user objects that users supply, move around with Python pickle as well. I think there's a lot of exploration there that could happen with sharing and caching. Right now, if you run 1 billion tasks, it's 1 billion copies of your 1 kilobyte user function that goes over the wire to workers. Pickle supports basically this kind of caching, that kind of stuff, but not in the way that we use pickle. So we don't get any benefit from that. I think there's lots of fun to be had there. Stuff like proxy store, how does that fit into the 1 billion task story? It should do, right? Like it's addressing some of these issues, or it should be. There's checkpointing, much neglected. What's the point of checkpointing? Well, two things: the resilience of a single workload, and the other thing is eliminating duplicate work in a similar workload. So I crossed out the second one because I don't care about it for this talk. But as your workflows get longer in real time, so if we're thinking about that 6-month workflow, it's much more likely that if you've got a single submit process, it's going to crash, it'll be killed. You're saying, oh, I want to run a workflow on this login node, please don't reboot your machine for 6 months. That becomes kind of inevitable that is going to happen just as a normal part of how your workflow gets run, right? Rather than, oh, this was a very awkward exception that doesn't normally happen. It will be completely normal for that to happen. So how do you make your workload outlive the lifetime of a single Linux kernel instance or a single Python process? Maybe you could put some stuff into a database, but then how does that interact with the language layer? That's basically what our Parsl checkpointing brings to this story. I'm not sure where it goes. Or you could go in a completely different direction. If you're completely cloud-brained, you could say, well, host your management process in this virtual machine in the cloud, and you get to control the lifetime. Then the process is guaranteed enough to stay alive, and you don't need any of that checkpointing. So that's a sort of completely different take on the same problem of making one workload resilient. Logging. In some of my tests, logging is absolutely the dominant overhead in what's going on. And everyone always has this cheat code when they're doing their nice performance graphs, which is you turn it all off and stuff runs much faster and your results look much better. But it's totally unsuitable if you're actually trying to debug things, especially if you're trying to debug scaling, stories around running, turning your logging off for big scale runs. Well, now you lose track of what's happening just at the point that you need to understand what's happening. So my claim is that you need that profiling even more at big scale, and the smaller scale, it's less relevant, which is kind of flipped from our traditional story. What does that look like when you're trying to not touch evil shared file systems? There's things like Chronolog. Those projects exist in some form. In the cloud world, there's lots of sort of observability experience. I think it mostly looks a bit more service-based, but it exists as a thing. So maybe there's ideas to steal there. And then the final bit of this is there's multi-site execution. For 25 years, I've heard people saying we're going to need it soon, but not yet. Basically because they never saturate their one supercomputer. Let's assume we need it. What's going to happen when you've saturated one site? What does actual real multi-site execution look like that isn't someone's PhD research, right? How do you select sites? How do you deal with management of tasks that run on one site and then get transferred somewhere else? All kinds of stuff like that. And this bit always feels to me like it's very poorly integrated because no one really pushes on making it work. Maybe in 8 years, we'll want to do this for real. So how might we get there? Whatever you imagine a goal of what I just talked about, imagine some goal in your head. How might we get there? So one thing is we would need, I think, to regard scalability as a real feature. So right now we don't regard it as a feature. Could someone, for example, estimate off the top of their head how many tasks I could have outstanding on my laptop just based on numbers, right? That you already know. Probably, maybe Yadu can, but it's not a generally known fact, right? Because it's not a thing we think about. How do we think about sort of CI style testing of scalability to stop regressions? Right now, when we review code, there's not a lot of thought going into does this damage scalability? We don't have any testing for that. That might look, one idea, for example, is maybe we got friendly sites like ALCF or NERSC. Once a month, we run as many nodes as they'll give us for 10 minutes just to see what happens. And try and do that on some allocation that's targeted at this, not trying to hide this inside someone's other science project. Maybe we have some dedicated hosts for doing more unit testing style performance benchmarks of individual components that we could run on every PI, right? But those are things we don't do now. So we have in the past had embarrassing, very embarrassing performance regressions. Definitely I have introduced some. So we don't, as well as not testing for regression, we also don't really have a good characteristic of what our limits look like now. So traditionally we've tended to say, I want to show you a graph that shows how good Parsl is, right? I don't want to show you a graph that shows you how bad Parsl is. And a lot of the application-based stuff has been driven when the application people complain about something, then we go and fix it for them. So then it's fixed and they stop complaining and we stop caring. So it's difficult to ask questions like, if we improve X, will we hit a limit somewhere else on component Y? Or if I scale up component Z or Z, will it still work? How do I know which ideas to work on, which ideas to push on, which components to push on? So that's a thing I think would be good for us to do. Another thing is on the human side is how does research feed back to scalable Parsl? So people do various things with Parsl. There's a sort of pattern that sometimes looks like you wrote a paper, you got your PhD and you moved on to something else. It would be nice if, in addition to that, those science results somehow improved Parsl a bit, right? Some way or another. So like TAPS, for example, Greg's thing, I'm kind of sad that it didn't result in lots of fixes in Parsl for problems that he discovered, right? But there was a bigger loop that was TAPS then was a useful exploratory tool for Matthew's interchange manager selection work. And we got some really nice output of that showed that it was worth productionizing it and putting extra effort into productionizing it. And so now Parsl benefits from that stuff, which is being merged at the moment. So sort of TAPS as a research tool played into that loop in quite a nice way. So you could ask, how do you use Parsl as a source of problems, and how do you use the solutions to those problems to go back into Parsl in a loop? How do we incentivize people to do that? And there's some more production-oriented co-conspirators. So Globus Compute, Desk, ALCF are 3 examples. Do they care? How much do they care? In which direction do they care? Who else might be interested in playing along? I had to put a little plug-in for plugins and modular code base because I think it's a very good way to get people to do stuff. So another thing, I mentioned it a bit before, how do we do when we do like application consulting or professional services stuff, which is where we put a lot of effort into helping someone get that application going, how does that loop round to also benefiting Parsl rather than just getting some hacks in place to make that application work by hook or by crook? Okay, so a good example is Desk has paid for a huge chunk of Parsl resilience because a lot of the work I did to fix up Parsl but then came back into trunk. Bad example is sort of historical FunkX, which forked the code base, made it arguably worse, and didn't feed anything back into core Parsl, right? So I think that was I'm glad that's not happening anymore, but that was a sort of direction that things can easily go into. So non-goals, don't rewrite everything from scratch. Here's some excuses because you're bored, because you think that people with clean minds won't make the mistakes of the last 25 years. You think your grad student could write this in a weekend. That's not a thing that I think is a good thing to do. And there's some other stuff that sort of lines up. They're not opposing goals, but they're sort of goals in different directions, just to bear in mind that they are slightly distinct. Things like training up students, just doing general science, implementing features for other purposes, maybe just trying to get contributions just so that people can say they've made a contribution or got a bullet point on their graph, things like that. Those are sort of pile of things that are around, but they don't particularly line up with this imagined future. So that's the end.